So now what we want to do is look at the basics of our substitution and elimination elements, okay? We're using elements here as the component pieces within it. If we take a look at the reaction shown across the top, this is our overview for a substitution reaction, not an elimination, and we know that because the elimination forms a pi bond and we don't have one being formed here. Okay, so if we go through and look, we do have some color coding. This is blue. We've got the leaving group, or LG, in purple. We've got the red nuke, and we have green for solvent. These pieces will always show up in substitution and elimination reactions. So we need to be able to look for these pieces whenever we look at a reaction. In this video, what we're going to do is take a look at the substrate kind of nomenclature and how that applies into our substitution and elimination reactions. Future videos will take a look at leaving groups, and another video will look at nucleophiles and bases, and another one at solvents. Okay, so the first thing we got to do is look for our big bulk classifications. We've got 4 structures on the right and conveniently 4 definitions on the left for each of these structures. We'll start at the bottom because that one's the least something. We've got a tertiary halide, okay, typically represented by the 3 and the little circle next to it, or degree next to it. What we're referencing is the carbon where the chemistry is located, okay? So that is our tertiary halide because we have a bromine there. That carbon is connected to 1, 2, 3 carbons, okay? This, by definition, is in reference to carbons, not other atoms. So, for instance, if I changed that 3 down there to an O, it's technically not a tertiary halide anymore. This author, I don't really necessarily agree with that because it removes some of the reactivity discussion behind it, but we need to be careful with that referencing, okay? So officially, we now have a tertiary halide. Secondary, well, similar idea. We find the carbon where the halide is located. In this case, we have a chloro. So chlorine, there's our carbon, and we look around it for how many carbons are located. In this case, the structures are a little bit different because we've seen a wedge now being added to our structure, and we're not showing the 4th bond to a hydrogen. Well, since it's a hydrogen, we don't really care because we only cared about the carbons. We've got these dots, and as we remember from the very beginning of first semester, dots are assumed carbons, which means that red carbon in the middle is a secondary because it's connected to 2 carbons. Okay? So on and so forth for our primary. And then officially, back at the top, we actually got to say it appropriately, it's the methyl halide. I prefer to refer to it as a zeroary. I can get laughed out of chemistry circles up wherever. Okay, that's fine. Okay, but I think it makes more sense if we're sticking with tertiary, secondary. Zeroary is the number of carbons. Zeroary makes sense because where the halogen is located, that carbon is connected to 0 other carbons. Okay, so those are our big substrate classifications. What we kind of want to get a feel for is how those can be affected in our substitution and elimination reactions. So on this slide, we've got them split. SN1 and E1 are grouped together as the stepped mechanisms. And then the simultaneous mechanisms are kind of split, you'll notice over there on the right, E2 and SN2. And that's because we have to make different discussions about these. For the stepped ones, SN1 and E1, there's a couple things that you should remember. Number one, when we say one type mechanisms or unimolecular, you should immediately be jumping to the term carbocation. Both the SN1 and the E1 form carbocations, which means when we're looking at a substrate effect for these mechanisms, we should be thinking about the carbocations that get formed from each of these individual substrates. Okay? Well, how does this end up affecting how our reaction occurs? Well, to do that, we would need to look at an energy diagram. And if we keep our focus on the blue one for the moment, all we're showing is the very first step. the formation of the carbocation. We aren't actually doing the next step. The next step would be something thereafter, ending either at elimination that's higher in energy or a substitution that's lower in energy than our reactant. Either way, we have to get to the carbocation first. Okay? So what we need to do is decide which of these would be easier to form. Well, this then goes back to stability of our carbocations, which you should remember from the previous video. The tertiary substrate, or the tertiary carbocation, is more stable than the zeroary, and so the tertiary should react faster than the secondary, faster than the primary, faster than the zeroary. Okay, why? Well, this is our energy diagram. The carbocation for the tertiary is more stable, and so it is lower in energy in our reaction, which means the activation barrier to form that cation is lower, which means I am more likely to form it. Okay? The other one is higher, making it less likely to go through and form. Okay? This is why when we run SN1 and E1 mechanisms, we tend to see tertiary substrates react very fast. Okay. Now that we got the basics for the SN1 and the E1 kind of out of the way, we can move on to the E2. Okay. When we move to the E2, we now need to again think about what's most important. Okay. Well, it is simultaneous. Okay. We could also bring in the term backside, but that's not what's going to drive this reaction. What's going to drive this reaction is that we need to form a stable pi bond. Okay? When we look at the E2, it is again going to be this endothermic reaction because the pi bond is higher in energy. Okay? So what we want to do is say, well, which of these would generate the more stable pi bond? If the pi bond was lower in energy, it's more likely to form. Okay? So what we could go through and do is with each of these substrates, do the elimination, remove the hydrogen, remove the leaving group, and put in a pi bond between those carbons. What you should notice is for the zeroary, it doesn't happen because there's not a second carbon. There's not a beta position to do an elimination. Okay, for the primary, we could do it. We can remove the chlorine and we could remove an implied hydrogen. For the secondary, same deal. For the tertiary, same deal. Okay, for the sake of my drawings, I went through and did it for only the primary and the tertiary. Okay? When we go through and look at those, we're still seeing kind of a substrate effect. But here what we're doing is evaluating the energy of the product in this. Okay? And in that case, what we've got to decide is what makes one or the other of those more or less stable. Because we'd assume the secondary sits somewhere in the middle. Okay, well, the thing that makes both of these reactive is that pi bond. Well, this is not technically correct. I like this explanation. For that pi bond to react, it has to leave the structure. Okay, the upper part of that carbon, we have no idea what's out there, but whatever it is the same for both, so we're going to ignore that half of the structure. And all we're going to do is look at the other half. For the primary, when the electrons come out, they have to avoid hydrogens. For the tertiary, when the electrons come out, they have to avoid carbons. So this goes back to kind of carbocation stability. How does carbon differ from hydrogen, and how is that going to affect our end result here? So number one, they differ because carbon has more electrons, 4 and 4 versus the 1 and 1. Okay. Well, what's the thing that's now going to be affecting these? Well, it's that arrow that we used. That nice little curved arrow, which is now referencing the motion of electrons. So which case is going to be easier for the electrons to leave the structure? One where those electrons could encounter just 2 or 8. Okay? That helps us to see that the tertiary pi bond is more stable than the primary. And if we color coded, we could even drop the secondary in between. Okay? And that's how the substrate affects the end result for the E2 elimination. What happens with the SN2? We can kind of cheat. Before we do that, this whole substitution effect, okay, is what is colloquially, pretty sure I butchered that, known as the Zaitsev's rule, okay, which I think is kind of dumb to reference it that way for multiple reasons. One, it's not a rule because it's not always followed. And if we evaluate the stability of these molecules, we don't need to name it after anybody. This is a pretty straightforward explanation for what's going on. We don't need to drop in somebody's name for this. Okay. Historical note, I lied. We'll put that in the next thing. So SN2, we should remember backside for backside attack, which means what we're going to do is take our nucleophile, the N from SN, and our nucleophile has negative charge, and attack the backside of that leaving group bond. Okay, and we might ask, well, how is the substrate going to affect this? Okay, well, what we're concerned about is what's on the backside. What's going to prevent the nucleophile from getting in there? Okay, well, the thing that's going to prevent it would be electrons. Okay, so we could go through and say, well, rough approximation, we could look at the anions. Which of the anions was more stable? Well, the more stable anion was the top. Why was that the most stable? Because there were fewer electrons around it. Wait a second, fewer electrons around it. Well, if there's fewer electrons, what does that mean for the ability of the nucleophile to attack the backside? Oh. Okay, so now let's take a look at some real structures. How might we predict these to react? Okay, so I will go through and run a test run here with SN1. So in SN1, I know I'm doing carbocations, so I want to think about what carbocation could form. Okay, what I could go through and do is draw this. If you're in first semester, you need to be drawing it. If you're in second semester, you should be able to start to internalize these drawings without having to draw them. If you don't feel you're there yet, draw the structures. Okay? For homework, just draw the structures anyway. You'll get used to it so that when it comes to the exam, you won't have to draw as much. Okay, so if we can now go through and evaluate these, we could go through and say for that bottom one, we have a primary because there's only one carbon connected. For that second one, we have a secondary because there's two carbons connected. And for the top one, we have a primary. So if we think about how we would expect our reactions to go, according to SN1, we might predict what? And again, predict based off the discussion we've had so far. Okay? In theory, we would predict that this would be a yes and both of these would be a no. For those of you being like, I got that answer wrong, okay, what did you add to your discussion of your analysis? Because you're right, all three of those answers are wrong. Okay? The concept that you added is that we can't look at just the substitution effect. Okay? And in fact, if you go back to the reactivity video, the substitution effect is the last thing we should be looking at. We should be considering resonance effects. And if we go through and evaluate, we have resonance for both the top one and the bottom one. That additional resonance makes that primary stable enough that it reacts in both cases. It makes it so reactive, it's actually more reactive than a tertiary. Okay? So what does that mean? Well, it's so reactive and it runs counter to what we would expect. We would throw in a name at it. The top one is typically referred to an allylic position, and the bottom one is referred to as a benzylic position. Okay? That extra resonance makes a huge effect in our carbocation stability. And in the second one, that ain't secondary. If you go back and look at our classifications, primary, secondary, tertiary, they're all referencing atoms that started sp3 hybridized. In this case, that's not sp3 hybridized, okay? Which means the classification of secondary is actually wrong. It is better classified as sp2 or vinylic. In either case, it shuts down the reactivity entirely. Okay? That is a trickier one to deal with and one that I don't really feel like talking about in this video. Okay? So if you have questions about that, feel free to shoot me an email or talk to me in class about it. Okay? And with that, we're at the end of our substrate video. Thanks for listening.